So we're continuing with section 4.7, example 8. Find the area of the largest isosceles triangle that can be inscribed in a circle of radius 1. So we're talking about maximizing the area of an isosceles triangle, and so the boundary of the circle is our constraint. And so the circle x squared plus y squared equal to 1, the fact that each vertex of the triangle is going to be sitting on that circle. So let's graph this. So circle x squared plus y squared equal to 1 and an isosceles triangle. And let's draw this isosceles triangle so that it would basically be symmetric about the x-axis. And so you see this is a triangle. The area of this triangle is, look at this point over here, x and y, and we see this more often to actually put something geometric on the xy plane and calculate things. It makes it a little easier to calculate. And let's say this x value is right here and y value is right there. You can see the height of the isosceles triangle is the radius of the circle plus x. So the height is, I'm finding the area, the height is 1 plus x, and the base is 2y plus y, 2y, divided by 2. That's the area that I'm trying to find. And then the constraint on this is x squared plus y squared equal to 1. And if I solve for y in here, I get y equal to plus minus square root of 1 minus x squared. But really, the minus doesn't count because we're talking about the lengths. Replace that y back in here, and let's take the derivative. By replacing y back in there, a of x is going to be 1/2 of 1 plus x times square root of 1 minus x squared. At this point, for taking a derivative, I suggest doing a product rule. After the product rule is done, what you want to do is you want to make a common denominator and simplify to have this shape. And from here, you can find all the critical values, and from critical values, we can find where the maximum area is attained. So one thing that is important to understand is that x can be maximum at 1, but if I put x at 1, then the area is going to be minimum, and x can be 0 also, and then that's the other end that we get for x. Or x negative is actually possible in here, but very soon we realize that the area is not going to be maximum for x minimum negative values. So let's try to figure out what are the critical numbers that I care for in here. So I have to solve 2x plus x minus 1 equal to 0, and then from here I get x equal to minus 1 plus minus square root of 1 plus 2 times 4, which is 8, divided by 4. That is negative 1 plus minus 3 divided by 4, which gives me 1/2 and negative 1. Negative 1 is going to give me area 0, so let's go with 1/2. and then using 1/2 we can figure out what value for y we get, and we can find the value for area. Plugging it back into the area function for 1/2, and we end up with 3 square root of 3 over 4. And since plugging in 0 and 1 is not going to give a bigger number, and -1 is not going to give a bigger number, that's the biggest number that we get, and that's the maximum area that we get. And so the largest area is approximately that much. Example 9. Boat A leaves the dock at 1 p.m., travels due north at speed of 20 km per hour. Boat B has been heading due west at 15 km per hour and reaches the same dock at 2 p.m. How many minutes after 1 p.m. were the two boats closest together? So how does this work? Boat A leaves the dock and goes to north at a certain speed, which is 15 km per hour, and then another boat who's heading west is going to reach it after 1 hour basically. And the question is, when were the two boats the closest together? One is going away from the dock, the other one is arriving at the dock. And so to find this, you have to find this distance, that distance, and then using a Pythagorean theorem, find the basically the distance at any point between the two of them, and use that to find the minimum distance possible. So the one that is coming, that was heading due west at 15 km per hour. I'm sorry, this was 20, the other one was 15 km per hour. Basically 1 hour before 1 p.m. this was 15 kilometers away, and so it starts from 15 kilometers, and then 15 km per hour, the distance is decreasing, so that's x. And then y and starts at 0 and goes 20 times t. So the distance between them is going to be the square root of 15 minus 15t to power 2 plus 20t to power 2. Now, this is the distance between them. One way of dealing with the problem is to take the derivative over here and find the critical numbers. I don't like the square root, so what I do is, instead of this, I know that distance is minimum when the square of the distance is minimum, so I just go to power 2, and instead of finding the maximum of the distance, I find the maximum of the square of the distance, which is this function. And so take the derivative of this, find the critical numbers, and critical number is going to be 9 over 25, and then find the beginning and end point for x. The x is defined on intervals 0 and 15, and with the critical number you can use the closed interval method and find the minimum value for d, and then square root of that value is going to give you the minimum distance basically. And so that's how this problem